In this presentation, I will be presenting my solution for predicting whether a person earns more or less than 50K per year using genetic programming. So we are going to look into these topics in this presentation, which includes problem overview, data preprocessing, GP parameters, GP components, primitive set, fitness function, deep setup, evolution process, best solution, ensemble approach, results, key takeaways. So first, let's go through the problem overview. We have a dataset called the adult income dataset, which includes 14 features like age, education, occupation, etc. And our goal is to predict whether someone earns more than 50K or below 50K per year. The training set has about 39,000 samples, and we need to predict outcomes for nearly 10,000 test samples. What makes this interesting is that the dataset is imbalanced, and about 76% of the samples in the dataset shows that the individuals earn less than 50K, and only 24% earn more than 50K. So to solve this problem, I have used GP. You might ask me why I used GP. Well, GP is really powerful for this kind of problems because it can automatically discover complex mathematical relationships between features without us having to manually engineer them, unlike any traditional machine learning uh, approaches. GP evolves tree-based expressions that combines uh, these features in creative ways, and it's like having an evolution discovery. So let's go through the data pre-processing. So first, I have included few libraries such as NumPy, Pandas, Matplotlib, and also 2 lines of code to suppress the warnings to make the notebook uh, cleaner. Okay, first we are loading the test and train dataset, and we are separating the features and target by dropping the income column from the training data, and we are also identifying the categorical columns and numerical columns. So let's go through the preprocessed data function. So first I handled the missing values. Some fields had question marks, so I replaced them with the most common value from the column using the mode function. Second, I have encoded categorical variables like work, class, and education using label encoding, using the label encoder library, um, which converts the text into numbers, which would be easier for the algorithm to interpret. Third, I created some feature interactions like multiplying age by education level and calculating the difference between uh, capital gains and loss. These gives the model more information to work with. So finally, I normalized all features using standard scalar, so they are on the same scale. This is important because GP operations work better when the values are comparable. Next, we are splitting the training data for validation, and the training set and validation set are being separated. So uh, let me walk you through the evolutionary parameters, that those are GP parameters. I have taken the population size of 300, crossover probability as 70%, so that the two parent swaps the subtrees to create offsprings, mutation probability of 20%. This randomly changes the trees to introduce new variations. I've taken the max generations as 100, the tournament size as 7, and the Hall of Fame size as 10, where we are storing the best individuals. And we are also using the random seed. So I also set the height limits for the trees, where the minimum height is 2 and the maximum height is 6. And also I have set the hard limit as 17 to prevent the trees from growing extremely large. Next, let's discuss the building blocks of our GP. Those are GP components, primitive set. I included basic arithmetic operations, addition, subtraction, multiplication, and protected division. Protected division is important because it avoids dividing by 0, which would crash our program. I also added comparison operators like greater than and less than, and if then else function for logical condition. For some complex operations, I included protected square root, protected logarithm, and a sigmoid function to normalize outputs between 0 and 1. The protected versions handles the edge cases. like taking the log of negative numbers. So evolution can explore more freely without errors. Each individual in our population is a tree uh, made of these primitive combined 16 features. So the fitness function is very crucial. It tells evolution what's good and what's bad. So my fitness function here does two things. First, it calculates the accuracy, like how many predictions the individual got correct. Second, it adds a small penalty based on tree size. This encourages simpler solutions and prevent bloating, which means it prevents the tree from growing extremely large. The formula I used here for fitness is accuracy minus the complexity penalty. So if the tree has a 95% accuracy and 50 nodes, the accuracy score would be 95 minus 5, which is 90% accuracy. This balances the performance with simplicity. Next, this is the deep setup where we are creating the individuals, registering the genetic operations and operators like selection, crossover, and mutation. And also we are creating a hall of fame to show the best individuals. Next, here is the evolution process, uh, where the evolution starts with an average accuracy of 50%, almost 50%, and gradually learning from the patterns and better guessing, it gains the accuracy of almost 78% of average fitness, and the best fitness that could be reached is approximately 80 to 82% of fitness, which is very solid. Uh, Next, so we have arrived at the best solution. Uh, as you can see, the expression for the best solution looks something like this. Uh, let's decode it. It is using capital gains in the smart way, taking the maximum of capital gains and the negative of occupation. Then it has conditional logic that checks if the capital gains are negative, and if so, uses education level instead. This makes intuitive sense. People with higher capital gains tend to earn more, and education level is also a strong predictor. The tree discovered these relationships automatically through evolution. I also tried an ensemble approach combining the top 5 individuals using weighted voting. The weights were based on each individual's fitness. Interestingly, the ensemble approach achieved the same accuracy as single best individual on the validation set, which was 84.07%. So the final predictions, uh, I went with the simpler approach of using just the best individual. So here are the final results. On the validation set, my GP solution achieved around 84.07 accuracy. That's really good accuracy. Looking at the test predictions, out of 9,769 samples, we predicted 8,175 as low income and 1,594 as high income. This roughly matches the distribution in the training data, which is a good sign. So finally, we are storing the predictions of the test dataset into a CSV file named predictions. So let's talk about the key takeaways. First, genetic programming proved really effective for uncovering useful features. It highlighted capital gains, occupation, and education as the strongest indicators of income, and it even captured the nonlinear interactions. Second, we learned that the accuracy isn't everything. Model simplicity matters too. By adding a complexity penalty, we prevented the trees from becoming unnecessarily large and avoiding bloating and overfitting. This pre-processing played a huge role. Uh, Encoding categorical variables properly, adding interaction features, and normalizing the data has significantly boosted the model's performance. And lastly, the evolutionary approach actually worked um, surprisingly well. Uh, we began with completely random trees, and through selection, crossover, mutation, the system evolved the model that reached over 84% accuracy. Thank you.